In this lab, we were looking at the magnetic field of a bar magnet, and the purpose of doing this was to measure the distance dependence of the magnetic field of a bar magnet for on and off-axis magnetic fields. We needed a strong bar magnet, magnetometer app on phone, meter stick, and tapes for this experiment. A brief introduction about the procedure was we had to locate the magnetometer chip on the device first, and then we found the distances for which the magnitude of Bx matched a specific value, and then we obtained n and calculated the magnitude of mu, which is the magnitude of magnetic moment. And lastly, we measured the magnetic field along the 45-degree axis, as you can see on the bottom right image, and we compared this with the computational value from GlowScript. Some fundamental physics principles that we used are Biot-Savart law for a dipole and distance dependence, which was mentioned in the experiment instruction. This is a table of the measurements. As you can see, we measured the average magnitude of Bx when it was equal to 20, 70, 120, 170, and 220 microteslas. And the Excel spreadsheet plotted this into a graph, and from this we got n as negative 2.9986 and ln of k equal to negative 14.53. We were able to see from this that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Using the values from the previous slide, we did some calculations to measure the magnitude of the magnetic moment. ln of k was measured to be negative 14.53, and we took the exponential of this to get k value of 4.894 times 10 to the negative 7. And then we plugged this into the dependence equation and got mu equal to 2.4472. And I've plugged this value into the GlowScript code that I had created. Then looking at some specific parts of my coding, I had to create a function called Dipole B using mu and r as parameters to calculate the magnetic field, as you can see on the right. And then I also repeated the setup of how to create an arrow representing magnetic fields at different locations. I created 2 for on-axis and 4 for off-axis. And lastly, I had to find the computational B field for 45-degree angle by using the code as shown. This is a computational model that I created, and the orange arrows represent the on-axis magnetic field, and the 4 cyan arrows represent the perpendicular axis, and the single pink arrow represents the 45-degree from axis. Comparing the value that I got from the computational model to my observation value, as you can see, my observation shows that B at 45 degree was 1.2 times 10 to the negative fifths, and negative 1.7 times 10 to the negative fifths, and negative 4.03 times 10 to the negative fifths. And this did not match the GlowScript model, where the z value had 0, and other values are also different as well. And one thing that could account for this difference is that in the model, we assumed that the Earth's magnetic field was 0, acting on the point. However, when we did the experiment on our own, there could have possibly been some Earth's magnetic field being applied to it. What if I hadn't oriented my experiment to compensate for magnetic north? The results that I calculated would have not been solely due to the magnetic field from the bar magnet, but instead it would include the Earth's magnetic field as well, and the measurements will be incorrect. And if I stuck two identical magnets together end to end and ran the experiment again, I would expect to see a much larger magnitude for the magnetic moment and magnetic field in the same direction. To conclude, I calculated the magnitude of magnetic moment to be 2.4472, and as the magnetometer moves closer to the magnet, we can conclude the measured x component of the magnetic field increases.